On verra. C'est pas prévu. Donc, j'ai pas compris si je parlais en français ou en anglais. Donc, en anglais. Okay. So, well, thanks for inviting me here. It's a pleasure to be back. And so, yeah, as Vincent said, I'm gonna talk about trendy things, generalized Gibbs ensembles. You might have heard at least the name. So yeah, it's been quite an active area of research in the last 5 years or so. So I will introduce the main perspectives and some of the progress that has been done recently. And actually, some of the progress has been done by some of us, so in collaboration, mostly with people in CISA and also Balázs Pozsgály in Budapest and Marcos Rigol in Penn State University. But the main part of this talk would be devoted on to the case of field theories, in particular the Sine-Gordon model. And this is basically what is contained in this paper, which I have written with Axel Cortés Cubero, who was a postdoc at CISA and now he's in Netherlands. Okay, so for those who don't know so much about the thematics, the main focus is basically the dynamics of isolated quantum systems. And the way people usually study dynamics is through what we call quantum quenches. So this is arguably the simplest way of studying dynamics. So you prepare an isolated quantum system, so which is all of this, in some initial state, which I call psi naught, and you let it evolve under the Hamiltonian H. So, of course, the whole state remains in some, the whole system remains in some pure states, but you should expect, of course, to have some kind of relaxation at long times. And in fact, what happens is the following picture. If you look at local observables within some subsystem, you can view actually the rest of the system act as some kind of environment. And so for generic systems, what you expect is that you will have some kind of thermalization of local observables. So this is some picture taken from some experimental paper of 2012, where you see that indeed local observables in a quantum quench, they first oscillate and then they stabilize to some value. And this value is well described by some effective statistical mechanics, namely by some Gibbs ensemble at some fixed temperature, which is fixed by the initial conditions. Okay, now the main point here is that in some systems you do not have thermalization. So the first and most famous experimental observation of such a phenomenon has been done in the so-called quantum Newton's cradle. So this is the experiment which is depicted here. Basically, so it's a cold atomic experiment. You start with one condensate of bosons, which you split in two, you give the two halves opposite momentum distributions, and you look at what happens. And what you would expect is that after a few oscillations, everything would collide, and you will end up with one given condensate at a zero average momentum in the middle of the well. But what was observed instead, so here is the time direction and here is the density of atoms, is that even at long times, after many oscillations, you don't have this kind of relaxation anymore. And this phenomenon was actually associated with the fact that such a system is almost integrable. So the point is that integrable systems do not thermalize. And when I mean integrable, I will specify a bit more later, but this means basically systems which have many local conserved charges. And these charges highly constrain the dynamics, so they forbid thermalization. And so it was proposed that in such systems, instead of thermalization, you should have instead some kind of generalized thermalization, so namely local observables at long times become described by such a statistical ensemble, which we call the Generalized Gibbs Ensemble, and which is made up out of all of the local charges. Okay, so this ensemble will be the main focus of this talk. But so before going further, let me just specify a bit more what I can mean by quantum integrable systems. So this can be of various nature. For instance, quantum spin chains. So here you have the example of the well-known Heisenberg spin chain. So you have a nearest neighbor interaction, and here's some anisotropy. So I will be considering this model a bit later. You can also have models of interacting bosons or fermions. So for instance, the famous Lieb-Liniger model with point-wise interactions. And you can also have quantum field theories. So for instance, the Sine-Gordon model, and I will spend a bit of this talk talking about this model. And it's actually nice to view quantum field theories in terms of particles. So basically you have particles in the one-dimensional space. They have some sets of rapidities, and the fact that the theories are integrable means that they interact through some factorized scattering, so which I depicted here. Okay, so now back to the GGE. So the main questions that came after this GG proposal by Rigal in 2008 are, first, of course, is the GG proposal correct? And second, how to build it in practice? Because I've been quite loose telling you, okay, you have to put some local charges in there, but you will see that it actually led to some debate, the question of which charges to include in the GG to properly describe the long-time behavior of local observables. And other question, how quantitatively different is it from the thermal ensemble in describing the behavior of local observables? So all these questions have been, as I told you, they've led to some intense efforts in the last 5-6 years or so, and there is still some ongoing debate. So I will present to you here some aspects, and well, we'll see that most of the progress has been done lately in the case of spin chains. So this is what I will be presenting in the first part of the talk, and then I will shift to new results that we've got in the case of field theories. Okay, so first spin chains, and so we'll focus on this really famous paradigmatic example, which is the Heisenberg spin chain. So once again, spin chain, nearest neighbor interactions, and you have some anisotropy here, which we parameterize in terms of some real number gamma. And so the fact that this model is integrable, as probably most of you know, has to do with the fact that this Hamiltonian is actually part of a more general family of objects, which we call the transfer matrices. So these are operators which also act on the Hilbert space of the spin chains, but now they're written as a trace on some auxiliary spin, which I here put in red. And so they're a trace of a product of operators, which we call the R matrices, which are written as follows. So they're associated to some statistical mechanics model, which is the famous six-vertex model. And these R matrices depend on some complex parameter, which is the so-called spectral parameter. And what's important is that for different spectral parameters, the transfer matrices commute with each other. So from these, you can generate commuting charges. So basically, the construction is the following. You take the logarithmic derivatives of the transfer matrix at 0 spectral parameter. And so you get a set of charges which commute with one another. And importantly, one of these charges is the Hamiltonian. So what you get is an infinite set of charges which commute with the Hamiltonian, so which are conserved. And what's fundamental here is that these charges, they are all local. So for instance, the nth charge, it's written as a sum of densities which act non-trivially only on subsets of fixed maximal length on the chain. And yeah, let me emphasize that really locality is important here because any model has many, as many as you want conserved charges, because you can take, for instance, the projectors on the eigenstates, but these are not local, these don't mean anything, so it's really important that, for physical purpose, that in integrable systems you have local conserved charges. Okay, so this construction is extremely well known, and so the first natural idea from there was to build was to build a generalized Gibbs ensemble from these charges. So basically, a matrix, a density matrix, which would take the following form, and I call it here local GG because you will see that it's actually not exactly the GG that we're looking for. And so, well, attempts were made to compare the results of the GG against numerical experiments, so for instance, DMRG or tensor network methods. And it was observed actually, so here I took 2 pictures from articles of 2014. It was observed that this GG actually fails at properly reproducing the stationary value of local observables. So here the curves are the numerics, and here the dashed lines, here this purple line and here the dashed lines here, are the predictions of the GG. So you can see that in some cases you have a clear mismatch. Yeah?
Can you tell a bit more about the Quench study?
So these are all quenches in the XXZ spin chain. And no, it's always starting from some given product initial state. So this, I think, is the dimer initial state. And this is some tilted ferromagnetic state. So this is the angle for which it's taken. Okay, so the GG, as I presented, fails in these cases, but people still, at this point, wanted to stick to the GG philosophy, and the logic was then, okay, if we want to cure this GG, we have to add more charges. And the solution came actually from initial works of Tomasz Prosen from Ljubljana in 2011, coming from quite a different motivation, coming from quantum transport, and actually also Vincent worked on these problems. So the solution is that you can actually build more conserved charges in such models. And these charges, they're not anymore derived from the transfer matrix, which I told you before. They're derived from some transfer matrices which have higher auxiliary spin. So here, still represented in red. So these auxiliary spin can be, so before we had the spin 1/2, but this can be spin 1, spin 3/2, and so on. And so you have a whole family of transfer matrices which still commute with one another and commute with the original transfer matrix. And so they're indexed by some integer j, which is basically twice the spin. So in particular, T1 is the transfer matrix that we had before. So for these new transfer matrices, you can do exactly the same thing as we did before. You define these kinds of charges. And well, they're not anymore local for j bigger than 1, but they still satisfy some form of locality, which we call quasi-locality. So quasi-locality, it's well-defined mathematically, but basically you can view it as follows. Now, a quasi-local charge is made out of terms which act as long range as you want on the spin chain, but as you increase the range, you will have some exponential decaying. Okay, so then from there, the proposal was to include these charges to the GG, and this was basically done by Prosen and one of his postdocs, Ilevsky, in 2015. And what was indeed observed is that what we call the complete GG now, build out all of these charges, works. It really reproduces precisely the stationary values of local observables. So I took these pictures from papers that, so a paper that we've written this summer, and this is also a paper, more recent paper of a few weeks ago, where basically we've seen that in some cases there is really a strong mismatch between the local GG predictions, so the old not cured GG, and the actual values predicted by the complete GG. So you could really see this in experiments, and I mean it answers the question that I asked before: is there a clear mismatch between the different ensembles that you can have? Yes, there is a clear mismatch. Sorry? What was the difference that you had shown? So here, okay, so here there's a bunch of numeric data, so it's a bit difficult to read, but basically here in red is the complete GG, and you see that it's in agreement with numerics, which is in blue and green, up to some error. But this is the prediction for the local GG, which includes only the strictly local charges. And if you were to consider the thermal ensemble, it would be even worse. It would be even far off. So I mean, the predictions are really different quantitatively. And on the left, you also have triangles and you have... Oh yeah, on the left, yeah, same thing. Here, these lines are the complete GG, and these lines are the GG built out of local charges. And if you were to take the Gibbs ensemble, it would be even further. Okay. So basically the story is that for spin chains, this complete GG works. And before moving to field theories, let me, okay, so yeah, this is the explanation I wanted to give. Let me give you another illustration of why actually this is so. And actually it will be useful for the rest of the talk. Basically an interpretation of why we have to add all these charges to the GG. And this interpretation comes from the so-called Quench action approach, which is an alternative approach to the GG that was introduced by Ko and Nestler in 2013. And basically the story of this approach is that you can actually replace all your stationary properties by a description in terms of one single representative eigenstate of the Hamiltonian. So basically, you have to find one eigenstate which you are able to find one eigenstate which will reproduce all the stationary expectation values of local observables. So basically, this is the conclusion of the Quench action approach. And so in the case of the XXZ model, the eigenstates, you know probably that they can be parameterized by the so-called Bethe-Ansatz construction. So basically, eigenstates are parameterized by a set of complex numbers, which are the so-called quasi-momenta or Bethe roots. So they're just a generalization of momenta to interacting systems. And so as the system is interacting, they're not individually quantified. They're really quantified through some set of coupled equations, which we call the Bethe equations. And in the thermodynamic limit, these Bethe roots assemble into regular patterns in the complex planes, which we call the strings. And so basically, you can have real roots, which we call the one strings. You can have two strings, three strings, and so on. So from there, in the thermodynamic limit, we conclude that eigenstates can be parameterized by a set of densities for each kind of strings, and also a set of densities for the holes associated to each kind of string. So just as the holes in the Fermi C for non-interacting systems. Okay, so from these 2 points, what we can get is that in order to describe the stationary properties of local observables from the Quench action, what we have to find is just the set of densities for each kind of strings associated to the representative eigenstates. So if there is a GG that works, it should be able to reproduce this whole complete set of densities. And actually, there was a picture which people called string chart duality that was understood recently in a paper of 2015, still by Indievsky and collaborators. And this picture is that you can find actually a set of linear relations between the densities of these various strings and some operators which are the generators of the quasi-local charges. And basically, you see that you have a correspondence between the degree of the strings and the index of the auxiliary spin that is used to build the charges. So from there, what you see is that if you limit yourselves to a generalized Gibbs ensemble which includes only the local charges, so j equals to 1, you will only get information about the real roots and you will not know anything about the strings. So this is why you miss some information about the stationary state. Okay? And so in practice, what you have to do now, if you consider quantum quench and want to get information about the stationary state, is you have to evaluate the expectation values of these charges on the initial states. So this might be very complicated, but in principle you can do. Then from there, straightforwardly you compute the densities using this set of linear relations. And from there, there is a set of, in some models, you can work out the expectation values of local observables, entanglement measures, and so on. So from there, you can get everything. And let me just mention a technical aspect, but which actually is important, is that for certain initial states, these densities actually satisfy a set of functional relations, which people who know about integrability will recognize as the so-called Y system, so which takes the following form. And so in practice, when you have this Y system, all you have to do is evaluate the first two densities, and from there you get everything. So it's fairly easy in the end. And why this Y system holds, actually, we could explain in another paper with Lorenzo Pieroli, Atsisa, and Balázs Poszgai. Okay, but this was just a technical aspect. Let me just sum up what we have for spin chains. So I showed you that we have this complete GG here, which includes charges labeled by two different indices. So one which is the degree of derivation, and one which is the auxiliary spin that you put in your transfer matrix. And so for j equals to 1, these charges are local. These are the well-known charges of quantum integrable systems. And for j bigger than 1, these charges are not local anymore. They're quasi-local, and they're in correspondence with the densities of strings. Okay, now let me move to field theories, for which, as we'll see, there is way less progress made. So, and what I will focus on is, as I told you before, the Sine-Gordon model. So it's defined by the following Lagrangian. And the reason I'm studying this model is that it's really an important model. It's really a paradigmatic model of interacting integrable quantum field theory, but it's also relevant in condensed matter. For instance, it appears in the low energy description of spin chains, spin ladders, and of cold atomic condensates. So it's really meaningful physically to study quantum quenches of such a model. And turning to the picture in terms of particles, which I told you about before, in the case of Sine-Gordon, you have actually two kinds of particles, the soliton and anti-soliton, which semi-classically you can see as a field configuration which interpolate between two adjacent minima of the field. And yeah, there is an attractive regime in which these soliton and anti-soliton can form bound states, but here we'll restrict to the repulsive regime, so you really have only two kinds of particles. Okay, so to proceed, we want to describe a bit more the structure of eigenstates for Sine-Gordon. And so first, for theories which are a bit simpler, which have only one type of particle, so for instance, Sine-Gordon or free theories, eigenstates are pretty easily quantized. Basically, they're parameterized by a set of momenta, and these momenta are quantized through a set of equations which are once again called the beta equations, which take this form. And so you have a simple expression for the energy of momentum for such states in terms of the rapidities. Now, in the case of Sine-Gordon, things are a bit more complicated because not only you have to specify for a state the set of rapidities, but you also have to specify the internal index of a particle, namely whether it is a soliton and anti-soliton. And the strategy that we use, it's actually well known and pretty useful, is to trade this model with non-diagonal scattering for a model with auxiliary particles, which we call the magnons, and which play the roles of waves. So here with rapidities, which I call lambda 1, lambda 2, and so on. And these waves, as they pass, they change the nature of particles from soliton to anti-solitons. So the construction of states is the following. You start from a reference state where all particles are solitons, and then you build states with magnons. It's just really similar to the beta ansatz, the coordinate beta ansatz construction in spin chains, for instance. So now for this construction, you have a set of beta equations which is more complicated because now you have quantization not only on the physical rapidities but also on the magnonic rapidities, and so you have two sets of equations which take this form. Okay, and now if we want to consider quantum quenches, and so the construction of a generalized Gibbs ensemble in this case, we have to wonder which are the local conserved charges that we have to consider. So I told you before about the Hamiltonian and momentum, which have fairly transparent expressions. Similarly, it's well known that you can build local conserved charges which have similar expressions but which are parameterized by an odd integer Lorentz spin, so which enters in this expression. So for any odd integer value of the Lorentz spins, you have such local conserved charges. But what you can see is that all of these charges do not know anything about the internal content of the particles. They don't know anything about whether the particles are solitons and anti-solitons. They only depend on their physical rapidities. So in other terms, they are blind to the configurations of magnons. So what this means is that if you build a GG from only these charges, you will not get any information, for instance, about operators which depend non-trivially on the internal content of the particles. So for instance, charged vertex operators. Let me just mention that, of course, there is a lot of relevant work on Sine-Gordon, which considered neutral operators and which led to beautiful results. But here we're really concerned about building something complete, which will be able to describe also the internal evolution of the particles. So to proceed in this direction, so we still have the logic that there should be a GG and we want to cure it, make it complete. And to proceed in this direction, we use the so-called light cone discretization of the Sine-Gordon model, so which was introduced originally by Desri and De Vega in '87. And actually the construction started from not exactly Sine-Gordon, but an equivalent, somehow equivalent model, which is a massive Turing model. And this model is basically a model of massive fermions. And the discretization goes as follows. It's not a discretization of time and space separately, but rather a discretization of space-time in a diagonal direction. So you have here a square lattice, And each edge of the square lattice is a word line for fermions. So it's either occupied or non-occupied by a fermion, and you will encode this by either an up-pointing or down-pointing arrows. And the interaction between fermions takes place at the vertices of the lattice. And what was shown by Desri and De Vega is that basically you will be able to reproduce the physics of Sine-Gordon if you put at the vertices the weights of the 6-vertex model, which I told you about earlier. And what you can see is that actually this diagonal setup, you can really reconstruct it from the 6-vertex transform matrix, which I told you about earlier. You just have to put some inhomogeneities on the lattice. So here I have some real parameter lambda, and so you stagger the vertical inhomogeneities on the lattice, and so you get this kind of geometry. And from there, you can really reproduce the light cone construction. And the correspondence between the momentum and Hamiltonian and the light cone and the transfer matrix is the following. Okay, so now in order to recover Sine-Gordon from there, you have to take a scaling limit. And I will actually describe the scaling limit from the point of view of beta roots because it's more, I mean, it's nicely illustrated. So I told you before about the beta on that solution of XXZ. Here you have just a staggering in addition, but it doesn't change so much the structure of the roots. You still have a ground state, which is a Fermi sea of real roots, here depicted in black. And on top of this ground state, you have excitations, which can be either holes in the Fermi sea, so here in white, or strings here in red. And all of these beta roots are quantified by these kind of equations. And so when you take the scaling limit, so the scaling limit corresponds to shrinking the lattice, so sending the lattice spacing delta to 0, at the same time taking the number of sites n to infinity, and sending the staggering lambda to infinity, such as you will have this quantity here, which will be fixed, and this quantity basically becomes the physical mass of the Sine-Gordon particles. And in terms of beta roots, what happens in this scaling limit is that the Fermi sea of real roots becomes the vacuum. The holes in the Fermi sea becomes the physical particles, and the strings become the magnons. And you can see actually that the rank of strings is diminished by 1. So this is a detail, but this is important. But so basically you have this picture. The holes become the particles, and the complex roots become the strings. Becomes the magnons, sorry. Okay, so now that we have this picture, we want to build to look for more charges in Sine-Gordon from this lattice discretization, and we do something which is very analogous to what was done in XXZ. We introduce higher spin transfer matrices. I mean, it can be, it's just a matter of staggering, but it can be defined really analogously as in the non-staggered case. And from there, we define some charges. So these are indexed by not only the derivation index n, the auxiliary index j, but also some plus or minus index, which depends on the parity with respect to time. So this is due to the light cone geometry. And what we can see is that on the lattice, for j equals to 1, these charges are local. So here I depicted the densities defined as follows as a function of the range, and you can see that all charges have a finite range. And for j bigger than 1, these charges are still quasi-local. So you have, as I told you before, an exponential decay of the density of the charges. And this exponential decay is parameterized by some length, psi j. And what's important is that when we take the scaling limit, so when we take lambda to infinity, this length psi remains finite. So what this means is that when you turn to the corresponding physical length in Sine-Gordon, which is obtained by multiplying by the lattice spacing, because psi is in units of the lattice spacing, you will get something which is vanishing. So what this means is that the charges that we have here in the Sine-Gordon limit, they become local charges. Okay, so we have a whole set of local charges, and now, well, we want to know a bit more about them. And what we can know about them is, for instance, how they act on Sine-Gordon state. So to understand this, we start from the expression of our charges. So these xj, I didn't tell, but they are basically just they still depend on the spectral parameter, but they're still quasi-local for a given range of the spectral parameter, and they're the generators for these charges. And we have an expression for these charges, these generators, in terms of the light cone Bethe roots, which looks as follows. And so from there, you can work out a scaling limit, and what you get is such an expression, which is basically an additive expression in terms of the densities of physical particles and of magnons. So now we want to look in a bit more detail at what are these functions here, namely how our charges depend on the particle densities and magnon densities. And let us first look at the simplest case, which is the case of local charges, so j equals to 1. So from there, a first observation is that you have a 0 contribution from the magnons. So all of these charges do not know anything about the internal structure. They do only know about the dynamical information, the physical rapidities. And the way they depend on the physical rapidities, well, here I parameterized it in terms of two functions, C plus or minus, which are basically cos and sinh. And so from there, what you can see is that you can extract a leading term which goes like, okay, all these cos and sin should be replaced by cos and sinh. Sorry, but you can extract the energy and the momentum, and by forming linear combination, you can basically extract all of the odd Lorentz spin charges I was telling you about before. So you recover all the known local charges of Sine-Gordon that we had before. And well, this construction is not new. Actually, there's a paper by Reshetkin and Hubert from '94 in which they make this comment. Okay, but so this is for the local charges. But what's new here is that when we turn to quasi-local charges, not only we have a non-zero magnonic contribution, so these charges are not blind to the internal structure, but also there is something peculiar here. You can extract terms which depend on the physical rapidities through some non-integer Lorentz spin dependence. So typically these charges will be charges of fractional Lorentz spin. Now, charges of fractional Lorentz spins were known previously in the Sine-Gordon literature. There are basically two known constructions. One is from Bernard and Leclerc in 1990. And basically what they did is they built a set of charges which are non-local and also non-commuting. So this has not so much to see with ours, which commute with one another. And there is another construction from Bajanov, Lukyanov, and Zamolodchikov in which, considering transfer matrices directly in the field theory setup, they constructed a set of commuting charges, so like ours, which are manifestly non-local. So they have a non-local expression. And what's important or reassuring is that both of these charges have exactly the same set of fractional spins as ours. So there might be some connection between the two. But yeah, let me emphasize that here we really have some manifest non-locality, while in our charges we clearly have locality. So a precise comparison of the two sets of charges will require some more work, and there are some directions, so inspired by discussions with Hubert or Gabor Takacs, and so, I mean, this is future work, but we have to investigate a bit more. But now, going back to the initial purpose, which is building a GG, well, what we have is that from these charges, we still have some kind of string charge duality equations. So we have relations between the densities, not only of magnons, but also of physical particles. No, sorry, not only of physical particles, but also of magnons, and the generators of these charges, which are in Sine-Gordon not quasi-local, but local. So we have these sets of equations. So this means that, in principle, the charges that we have here should be enough to specify all information about the stationary state. So they should be enough to build a complete GG. So really, I emphasize that this is only in principle, because in practice, if we want to build a GG from there, we need to be able, for instance, starting from a given initial state, to evaluate these charges on the initial state. And this is something that we cannot do for the moment, because what I've showed you is the expression of the eigenvalues of these charges on the Sine-Gordon eigenvalues. But so we do not have yet an operatorial expression of these charges, so this still requires some work. But in principle, everything is here. Okay, now I don't know how. Okay, I still have some chatting after, but I'm pretty early. But basically, let me come to the conclusions. So for integrable spin chains, I showed you that there is now a fair agreement that a complete GG should be formulated in terms not only of local charges built from the fundamental transfer matrix, but also quasi-local charges built out of higher spin transfer matrices. So J equals to 1 local charges and J is bigger than 1 quasi-local charges, which are in correspondence with the density of strings. Now, in the case of field theories, things are a bit less elucidated, and what we have shown here is that in the case of theories with non-diagonal scattering, we can similarly build additional charges which come from the lattice quasi-local charges and which encode the distribution of magnons. So all the ingredients for a complete GG are there, except for what I told you before, that it's difficult in practice to evaluate these charges on arbitrary initial states. But there are some directions that we could follow. Okay, and now, yeah, so also an interesting aspect for Sine-Gordon by itself is that we have new local charges which have a fractional Lorentz spin, so it's quite unusual. So in particular, they do not satisfy the usual bootstrap equation. So, I mean, there's more to be understood about these charges, and it should be helpful to understand a bit more their relations between the previously known non-local charges, putting non-local between, how do you call that? Between? Quotes. Between quotes, because despite their manifest non-locality, there might be actually local, and so this needs more investigation. Okay, so there I am for GGE, and before concluding, let me just mention to you one possible direction. So everything I've been telling you about now is about stationary properties, but there is also some big concern about dynamical evolution. So the dynamics, it has many, I mean, it's interesting by many respects. For instance, there is a newly emerged field of dynamical phase transition, so in which people study the non-analyticities of observables as a function of time. And so what we've done recently with Lorenzo and Balash is study analytically, using integrable systems, the evolution of one simpler observables, which is the Loschmidt echo. So here are our predictions, and you compare here in dashed with numerical simulations, which really perfectly match until some Fanix effects take over. Well, yeah, there is really a lot to be investigated in this direction, because there is really little analytical results for the time evolution from integrable systems, and so we hope that we can extend this kind of method to more general observables, local observables, and so on. And so if you're interested, I'll be giving a seminar in Orsay January 19th, so not this week, but a week after, Thursday, I think. And with this, yeah, let me conclude. Thank you for your attention. Yeah, sorry I've been so fast.
So in retrospect, could you construct those kinds of quantities directly in the field theory limits, or do you always need a lattice regularization or something?
That's what we want to investigate, actually, because in the field theory limits, what you can do is you can start from these Bajanov-Lukyanov Zamochikov charges, in which really they have directly field theory transfer matrices, and from there they build charges. Our opinion is that there might be some relation between our charges and theirs, perhaps some kind of linear relations or something, and this, I mean, we can investigate by other means. And if we were to indeed observe that there is a relation between the two, then we could use these charges to get a relation between the two. But for the moment, I have no positive answer.
I want to take another field theory, and like right now the recipe would be always to go back to the lattice.
Well, yeah, I mean, the thing is that from the lattice we can really get a clear statement about locality. I mean, we can observe locality on the lattice. In field theory, so in this Bajanov-Lukyanov-Zamochikov paper, it's, I mean, in my opinion, and also I discussed with some people who agree, it's almost impossible to know about locality. I mean, you cannot say whether the charges are local or not. So, as far as I know, yeah, for the moment the recipe is to go back to the lattice. But they call them non-local because they have a non-local manifest non-local expression. But who knows? Yeah. But I mean, who knows if you could take? I mean, what we suspect is that there might be some linear relation, and taking a linear combination of these charges, you might end up by some miracle, or to some. You might end up with something local. But well, to be investigated.
Now, how about thermalizing a conformal field theory? I mean, why do Sine-Gordon?
Well, in things are, well, you don't thermalize a conformal field theory first because, I mean, conformal.
If I take a free boson and do the quench, do I get the GG or something?
Yeah, you will get a GG which is somehow trivial in the sense that the story of quantum quenches is basically that the initial state will create a lot of excitations which propagate in the system, and these excitations are quasi-particles, and in the case of the free boson, these excitations will propagate and not interact with one another. So we'll get something really trivial which is really specified by the rapidity distribution that you have in the beginning. No. I mean, so there is also this recent works on, for instance, on by Bernard, Doyon, and so on systems of two conformal field theories which you join at temperatures T1 and T2. What you see is that you have left and right movers, and the left and right movers do not interact, so they will continue propagating. And so what you have is a not trivial, but I mean, it's a clear.
Something I missed. If you do the same quench with XXZ in the regime where the theory is critical,
Yes.
then you have thermalization. But if you do it with the theory,
No, you don't have thermalization in any case because XXZ is integrable.
but you said it thermalizes to GG.
Okay, so that's what you call thermalization.
Sure. I mean, this GG is that, well, physically it's kind of I mean, it's interesting to look for the conserved quantities, but it's still a thermalization.
Yeah. Okay. Well.
Plenty of conserved quantities instead of the energy.
Yeah. Okay. You call it thermalization if you want.
XXZ thermalizing.
Yes.
CFT does not.
Well, CFT thermalizes to some kind of trivial, between quotes, GG in the sense that it's specified by. I mean, you can specify it either in terms of local quantities, as you do in XXZ, but in the case of CFT, what you will have is a distribution of rapidities for right movers and left movers, and these remain conserved with time. So you can re-express everything in terms of these, and the two pictures are equivalent in the case of free systems or CFTs, but in general they will not be. But so, I mean, it's still a kind of GG that holds in the conformal case.
You need only two conserved quantities, like for the Doyon and Bernard.
In this case,
You just need Hamiltonian and momentum.
yeah, I think that's really a feature of the free.
Yeah, I mean, you just have left movement.
Yeah.
Temperature of right movement.
Yeah. So it's a kind of trivial GG in some sense.
Well, what you have this philosophical idea that you can describe your state by describing some state in the spectrum.
Yeah.
Is that always the case? Or,
Well, there is. Yeah. There is this so-called eigenstate thermalization hypothesis, or generalized eigenstate thermalization hypothesis in the kind of integrable systems, which states that all eigenstates which are parametrized by the same values of the energy and local conserved charges will have the same local properties. So what this means is that you can take any eigenstates with a given set of these parameters, and it will properly reproduce your stationary properties. So when I was telling you that to specify an eigenstate, what you have to specify is the set of rapidities for strings and holes. It's not rigorously true because you know that a set of rapidities corresponds to a lot of many micro states, just corresponding to some rearranging. But the statement of the eigenstate thermalization hypothesis is that all of these states if they have the same, if they correspond to the same value of local charges, they will have the same local properties. So you can basically take any of them. It's not trivial at all, but it's actually believed and observed so far. Yeah.
When people say GG works, I don't find it super convincing.
In which sense?
Where there's wiggles, you clearly see that there'll be more wiggles if you wait more, if you don't wait more. And then you're looking at some operators. Can you comment on that? I mean, is it
You're looking, I mean, you're looking at what can be computed in practice. Things are extremely limited by the, yeah, you're extremely limited by the capacities of the MRG and this, and it,
so up there, for instance, it's the wiggles don't really die off.
yeah, sure. I mean, you have.
Suppose there's a recurrence theorem because the system is finite, right?
Oh, okay, no, that's something different. What you, in these kinds of systems, what you assume is always that you have first the thermodynamic limit.
Sure, I understand you assume it, but when you do simulation,
Yeah, when you do simulation, in practice, at some point you will have some recurrence, but
so you will suppose you are way before this occurs.
yes, I don't know how people who do the MRG in practice
Because
deal with this.
30 is kind of long, huh? I don't know how big the system
Yeah, but the system is, the system people deal with in the MRGs. I'm even wondering whether ain't. Yeah, there is a way in the MRG to just forget about the boundary conditions, and so. Yeah. But sure, yeah, if you do exact diagonalization, you'll stop basically at this point, and then you will have revivals and all these kinds of things. Yeah, so everything is limited by what we can get numerically, and that's also one of the motivations for the analytical calculations I was advertising in the end. But then, I don't know, we're wondering for which observables it works?
Yeah, which of,
Well, the statement is really for all local observables you should have this. More precisely, the picture is that if you have your whole system and you want to look at some observable which has support on some size R, you basically, I mean, to describe it precisely, to describe its stationary properties precisely, you have to include all the local charges which have a range which covers this length precise. But okay, there are some exceptions to this statement, but they're really associated to some kind of additional symmetries, and I mean some aspects which don't ruin the philosophy of the GG by any respect. So the J in practice you will restrict it to something like 20, and N is not. I mean, we don't use explicitly this kind of formula. What we do is instead, from the conservation of these charges, we'll work out some kind of TBA-like equations, but TBA is built only from the conservation of energy. Here you include the conservation of all these charges, so it's a bit more general. But so these TBA equations, they really include all of the ranges of n, and then you restrict to some value of j, and j is restricted to something like 20 in practice, and it works very well. But earlier people tried to really apply this formula directly, and I don't have a precise idea where they stopped, but basically this is the idea I was telling you about. If you want to compute, say, on the spin chains of some correlator between spin 1 and spin 3, I guess if you take observables with a range which is twice this, like 6, you will get really quantitative information. But well, I don't know the details about really applying this formula exactly, because this is what people were doing before, but this is extremely complicated in practice, computationally, and by many respects. Well, somehow what we use is really is similar to the TBA. So take in account the conservation of these charges, and from there solve some maximization equations. So basically what you get is a set of densities which are the densities of the representative states. So it's not rigorously applying this formula, but the spirit is the same. De rien. Merci.